Hello, in this video I'm going to go through how to work with surds in fractions, including how to rationalise a denominator, which takes us right the way up to high level 9 at GCSE and is also a really important skill that's going to come into lots and lots of things at A level as well. So first of all, I want to talk about something that a lot of people miss out actually, which is really useful thing to see. I'm going to go through a couple of examples where the square roots come out nice whole numbers so we can see how it works, and then we'll talk about using it for more difficult ones. So here are a couple of my favourite examples because these numbers are all square, so we can actually work out what the values are. So root 36, hopefully you're happy, is 6. The square root of 4 is 2. So root 36 over root 4 is the same as me saying 6 over 2, or 6 divided by 2. So the answer is going to be 3. The answer to this, if you put it into a calculator, would be 3. If I wanted to write that as a square root, though, 3 can be written as the square root of 9. So root 36 over root 4 is 3, or in other words, the square root of 9. If you now look at this, you'll notice 36 divided by 4 is 9, which is really nice. Okay, so there's a little pattern that we see with surds. Just like with multiplying, you can divide them to get one surd. Let's have a look at another example where we know the values. The square root of 100 is 10. The square root of 25 is 5. So we're doing 10 divided by 5, which we know is 2. Now 2 is the same as root 4. So root 100 over root 25, we know has to come out as 2, or in other words, root 4. And again, you'll see that pattern happening again here. Root of 100 divided by root 25 is the same as square root of 100 divided by 25, or 4. So you can just divide these numbers in order to get what you've got here. So now we can look at some where the numbers don't come out nicely for us to check. If I had root 12 over root 4, I could write that as the square root of 12 divided by 4, or in other words, the square root of 3, because 12 divided by 4 is 3. For the next one, root 20 over root 5, I can work out that as the square root of 20 over 5, or 20 divided by 5. 20 divided by 5 is 4, so it's root 4. Believe it or not, root 20 over root 5 is root 4, which can also be written as 2. Okay, and you can check those on calculators just to make sure you're happy that that definitely is going to work. So I've got a few questions for you to do on this, and we're using the rule that root something divided by root something else is the same as 1 square root of the two numbers divided. Okay? So I've just got a few questions for you to have a think about here. Pause the video and I'll go through them in just a moment. Okay, so here are the answers to these ones. We're going to do the square root of 18 divided by 2, which is root 9, and root 9 comes out as 3. Next one, root 30 over root 6 is root of 30 over 6, or root 5. Can't do anything with that, that's a surd. Okay, next up, root 40 over root 5 is root 40 over 5, which is root 8, and I can simplify root 8 to 2 root 2. As you get more practice with surds, there'll be a few that you just look at and know. Root 8 is one of them because you see it so much. Next one, root 72 over root 6 is the same as root 72 divided by 6. 72 divided by 6 is 12. And again, root 12 can be simplified to 2 root 3. That's another one of those ones that if you do a lot of surds work, you will start to recognise because it comes out quite a bit. So next up, we need to talk about rationalising a denominator. A denominator, as hopefully you already know, is the bottom of a fraction, so the number on the bottom. You'll notice in all these examples, I have a surd on the bottom, which means that the denominator is irrational. A surd is an irrational number. It's a decimal that goes on forever. If I'm asked to rationalise the denominator, I'm asked to change it so it's no longer a surd on the bottom, no longer an irrational number. We're going to aim for an integer instead. And we're going to do this using equivalent fractions. Now, hopefully you know that if you times the top and the bottom of the fraction by the same thing, you will end up with an equivalent fraction, which means it's the same answer. So the question is, what can I times by on the bottom here to make it come out as the same value? And the answer is, I can times both of them by root 5. Root 5 times root 5, if you can remember from earlier on in the series of videos, comes out as 5. So I'm going to times the top and bottom by root 5. Root 5 times root 5 is root 25 or 5. And on the top, 1 times root 5 is root 5. I've still got a surd involved. I can't get rid of a surd altogether, but what I have done is got the denominator to a rational number. Next one. In order to get rid of the root 3 on the bottom, I'm going to times the top and the bottom by root 3. 2 times root 3 is 2 root 3. Root 3 times root 3 is root 9, which is 3. Next one. I'm going to times the top and the bottom here by root 2. 4 times root 2 is 4 root 2. Root 2 times root 2 is 2. Now, looking at this fraction, I can go further. I can simplify it. I've got 4 here and a 2, which are both even. So I can actually half the top of mine to get 2 root 2's, and I can half the bottom to make it a 1. 2 root 2 over 1 is just 2 root 2. So once you've done your rationalising, always look to see if you can do any simplifying as well. Next one, I'm going to times top and bottom by root 3. So I'm going to get 6 root 3. Root 3 times root 3 is root 9 or 3. And again, with this one I can simplify because 6 and 3 are both in the 3 times table. So that can become a 2, that can become a 1. So I've got 2 root 3 over 1 or just 2 root 3. Okay, I've got a few questions just like these ones for you to have a go at now. So, oops. Sorry. Here we go. Have a go at those 4, and when you're finished, unpause the video and I'll go through the answers. Okay, so here are the answers. For the first one, you should have times by root 2 over root 2 and got 7 root 2 over 2. For the next one, we're timesing by root 3 over root 3 to get 4 root 3 over 3. Next one, we're timesing by root 2 over root 2 to get 10 root 2 over 2. These can be cancelled down to become 5 root 2 over 1 or 5 root 2. And the last one, we've got root 8 over root 6. We're going to times by root 6 over root 6. Root 8 times root 6 is the same as 8 times 6 with a square root over it, so that's root 48. Root 6 times root 6 is 6. Now we need to keep going here because we need to simplify our surd. Root 48 can be simplified to 4 root 3. You don't have to be able to do that in your head, you can take your time to do that. So it's 4 root 3 over 6. These can both be halved, so I can divide that, become a 2, half that, become a 3. So it's 2 root 3 over 3. So that's at the bottom there. Okay, so those are the simplest ones we can deal with. Now let's have a look at some slightly more complicated ones that follow the same idea. So for these ones here, you'll notice I've still got a surd on the bottom, but this time I've got something with it just to make it a little bit more complicated, or maybe something a little bit more complicated going on the top. So for the first one, I need to get rid of the root 3 on the bottom. I'm going to do that by timesing top and bottom by root 3. 9 times root 3 is 9 root 3. Now for this bit on the bottom, feel free to take it apart. So I can write it as 2 times root 3 times root 3. Root 3 times root 3 is 3. 2 times that gets us 6. I can cancel the 9 and the 6 down to get 3 root 3 over 2. For the next one, I'm timesing by root 6 on top and bottom. So I get root 30 over 6. Okay, I can't simplify root 30 down because there are no square numbers that are factors of 30, so I leave it at that. Next one, I'm timesing top and bottom by root 2. So I'm going to get 8 root 2. And then I've got 3 times root 2 times root 2. Root 2 times root 2 is 2. Times by 3 is 6. So I've got 8 root 2 over 6. I can cancel these down to make it 4 root 2 over 3. And that's my answer for that one. Last one, I've got some adding going on. So when I times the entire top of this fraction, I'm going to write a bracket in to make it really, really clear that that's what I'm doing. So I'm timesing by root 3 on the top and bottom. Now I would probably write this in an exam as root 3, 2 plus root 5, and then root 3 times root 3 on the bottom. When we simplify it, we're going to get 2 root 3 plus root 15 on the top and 3 on the bottom. Okay, I've got a few of these ones for you to have a little look at. Just 3 of these ones. So, sorry, I'll just make this a bit clearer for you. Okay, so have a go at those, and once you think you've got them, play the video and I'll go through the answers. Okay, here we go. Second one, I'm timesing top and bottom by root 3. I can cancel by dividing both by 3. And then this one. Now I'm timesing by 4 root 2, but because this on the top says 6 minus root 3, I'm going to put a bracket in, okay? Sorry, just timesing by root 2. This is not a very clear example now, is it? Sorry. So I've got root 2 times 6, which is 6 root 2. Root 2 times root 3, which is minus root 6. And then on the bottom, 4 root 2 times root 2, which is 4 times 2, or 8. I can't simplify this because although these two both divide by 2, this bit doesn't. So I can't divide every single term by 2. So that bit gets left as it is. Before I finish this video, I just want to talk you through very briefly how to rationalise a tricky denominator where you have to use difference of two surds. This is in itself quite a tricky part of the topic. It's the highest bit that you'll have to do in Surds, and it's very, very useful in lots of other places, so you will see it coming into other things. I'm just going to go through 2 examples to show you the trick, but this is something you'll want to go away and do lots more practice of because it's something that's quite complicated. Whenever you have adding or subtracting going on the bottom, there isn't something simple you can times by. So for example here, you can't just times top and bottom by root 5. That will not get rid of surds on the bottom if you times it through properly. So instead, I'm going to use the complement of 2 plus root 5. You might know, from if you've done your difference of 2 squares, that the complement looks exactly the same, it just has a different symbol in the middle there. So I'm going to times the top and bottom by 2 minus root 5. I'm going to put brackets around them so I remember that I'm expanding brackets. So on the top I'm doing 1 times that, so I just have 2 minus root 5. On the bottom I've got to multiply these out. Now if you want to, you can expand it out and simplify it, that's fine. If you're confident with difference of 2 squares, you might know you can do 2 squared, which is 4, minus root 5 squared, which is 5. 4 take away 5 is minus 1. Sorry. Now, because I've got minuses here, I'm going to do something just to make it look a little bit neater. I'm going to take a factor of minus 1 out of the top and make it minus 2 plus root 5. Because then I can cancel the minuses and end up with minus 2 plus root 5 or root 5 minus 2. Okay? Okay, so for this one, I'm timesing top and bottom by the complement, so 4 plus root 3. And again, I'm going to pop brackets around everything so it's really clear what I'm doing. So I've now got to do 6 times this bracket. So 6 times 4 is 24. 6 times root 3 is 6 root 3. And then on the bottom, you can either expand out and simplify, or if you're confident with your difference of 2 squares, 4 squared is 16. Root 3 squared is 3. So 16 minus 3 on the bottom, which comes out as 13. So I've got 24 plus 6 root 3 all over 13. Okay,